All right, today we've got a fantastic digital detective story for you. It's about a really stubborn piece of hardware, a super mysterious bug, and one developer's incredible quest to fix a problem that was, well, literally hard-coded into the machine. So at the very heart of our story is this tiny single-board computer. It's small, but surprisingly powerful. The only problem? It had this secret flaw that made it almost completely unusable. It would just freeze. No warning, no error, nothing. It would just stop dead in its tracks. So that begs the question, right? How in the world do you fix a problem when the blueprint is totally locked away in a black box? Well, as we're about to see, the solution wasn't about using brute force. It was about a clever, really elegant piece of code that completely changed the game. Okay, let's really dive into this. The computer we're talking about is the Orange Pi H3. For its size, it's a beast of a machine, especially with its Mali 400 GPU. But users started running into this deeply frustrating problem. Whenever you put it under a heavy load, it would just freeze up. So here's what was happening. Imagine you're running something graphically intense, and then boom, out of nowhere, everything just locks up for maybe 10, even 30 seconds. The logs showed this really weird cycle. The temperature would shoot way up, past 90 degrees Celsius, the whole system would freeze solid, and then, after that long pause, it would finally cool back down. Bizarre, right? So the investigation pretty quickly zeroed in on the GPU's safety system. Now, this is a feature that's designed to prevent the chip from overheating by slowing itself down. It's a process we call thermal throttling. But in this case, the very thing meant to protect the computer was actually breaking it. And just to be clear, thermal throttling is normally a good thing. It's basically your computer saying, whoa, hey, I'm getting way too hot here. I'm just going to slow down for a second to avoid any permanent damage. So what was the issue? It wasn't that it was throttling. It was how it was doing it. This whole digital ghost hunt led to one very specific file, dll.co. This is what's known as a kernel module, or you can just think of it as the driver. It's the file that tells the operating system how to talk to the GPU, and it holds all the rules for managing the hardware, including those thermal throttling rules. And this, right here, is where our detective hit a massive brick wall. See, the Mali code driver is closed source. That means the code is a secret. It's compiled into a black box. You can't just pop it open and look at the logic inside. It's kind of like trying to fix a car engine, but the hood is welded completely shut. So how did our developer get around this? I mean, you can't read the source code. Well, you have to do the next best thing. You have to reverse engineer the compiled file. This is like taking a car apart piece by piece, bolt by bolt, to figure out how it was built, all without ever seeing the original blueprints. Using these special tools called disassemblers, which basically translate machine code back into something a human can sort of read, the developers started digging through millions of lines of code. They were looking for any little clue, anything related to temperature or clock frequency. The goal was to find the exact instructions that were telling the GPU to slow down so dramatically. And then they found it. And you know what? It wasn't some super complex algorithm. It was something much, much simpler, hidden right there in plain sight. A tiny 16-byte table of numbers, just 4 simple values that defined exactly how the GPU should behave at different temperatures. Okay, this slide right here lays the whole problem bare. This is the table thermal_control freak that was controlling everything. As you can see, as the temperature goes up, the frequency steps down. Pretty standard. Mode 0 is cool and fast. But look at mode 3. When the temperature goes above 89 degrees, the frequency absolutely plummets all the way down to 120 megahertz. And that right there was the fatal flaw. 120 megahertz. For this specific piece of hardware, that speed was just so incredibly slow, it couldn't even keep the system running. It created this massive bottleneck on the memory bus, which starved the rest of the system of data and caused the whole thing to seize up. The protective feature was literally freezing the computer. So, you've found the problem, but it's locked inside a closed source file. You can't just edit it and call it a day. So what do? Well, you write a patch, a whole separate piece of code that can reach into the system's memory and change the rules on the fly. The solution came in the form of a custom kernel module named Imuna. A kernel module is kind of like a super powerful plugin for your operating system.
You can load it at any time to add new features or, in this case, to modify existing behavior, all without having to recompile the entire OS or that original driver. It's a small, targeted fix.
And this slide just illustrates the fix so perfectly. On the left, you've got the original flawed table with that dangerously low 120 megahertz floor, and on the right, you've got the new table that Amuna injects. Notice the critical change. The lowest possible frequency is now 200 megahertz, a speed the system can actually handle without freezing up. Brilliant.
So here's how it actually works. When you load the Amuna module, it first goes on a little hunt through the computer's memory to find the exact location of that faulty table. Then it saves a copy of the original values, which is always a smart move, and it simply writes the new, safer values directly over the old ones. It's like a surgical strike on the problem without having to touch any of the surrounding code. The project even got its own motto, La Amuna no se trotelea, which basically translates to the Amuna doesn't throttle. It's this defiant little statement that just perfectly captures the spirit of the fix. Building resilience and refusing to let a flawed design bring the whole system to its knees. So why did we want to share this story with you? Because it's about so much more than just one tiny computer or a few lines of code. It's really a lesson in problem solving and, honestly, in empowerment. This story really shows that with enough curiosity and determination, a single person can figure out and fix a problem, even when it's hidden inside a black box. And that fix doesn't just help one person, it gets shared with the community, helping thousands of others. And it's just this powerful reminder of why open source software is so important. It empowers all of us to be problem solvers. And that brings us to our final thought. This entire journey started with someone just refusing to accept that a problem was unfixable. It all started with this simple question, why? So I'll leave you with this. What frustrating, seemingly unfixable problems exist in your world that might just be waiting for you to get curious and ask why? Thanks for tuning in.